In my previous video on lunar roads, many viewers asked, why not use rail instead? Today, I'll explore Northrop Grumman's concept for a lunar rail network designed to speed up surface travel on the Moon as part of DARPA's 10-year Lunar Architecture Capability Study. Northrop Grumman, one of over a dozen selected companies, proposed building a lunar rail network. Past lunar missions landed rovers, power systems, and communication tools only to abandon them on the Moon, an expensive way of exploring other worlds. A rail network offers a sustainable solution, enabling fast transit of cargo and crew for scientific and commercial missions. The study calculates that a lunar rail network could unlock between $2 billion and $15 billion in economic value by 2035, driven by fuel transport, scientific research, and tourism. By leveraging local lunar resources for construction, costly Earth supply missions are reduced. Northrop Grumman plans to use autonomous robots for ground preparation and construction, reducing human labour in the harsh lunar environment. They propose a phased approach, starting with a test track and then expanding to operational routes, eventually spanning from pole to pole. Why not roads? Let's look at some of the challenges with only using roads for travelling around the Moon. Challenges with roads. Roads will likely be among the first infrastructure built on the Moon, offering a simple way to move across the surface. Still, they have some drawbacks. Let's go over each problem and look at how a rail network can reduce or eliminate it. Dust. Lunar dust, composed of ultra-fine, jagged, electrostatically charged particles, poses a major challenge. During Apollo missions, dust clung to astronaut suits and equipment, while recent lunar rovers faced dust ingress that shortened component lifespans. On unprepared ground, rovers kick up dust clouds as their tires churn the loose soil. These plumes can coat nearby habitats, scientific instruments, or solar panels, reducing visibility, damaging seals, bearings, and optics, and causing overheating by clogging cooling systems. The dust's abrasive nature also infiltrates mechanical systems, increasing friction and wear. A rail network, by contrast, drastically reduces dust generation. Trains run on elevated or embedded tracks, prepared through levelling, debris clearance, compaction, and sintering before rail track installation. This minimises direct contact with loose regolith, cutting dust production to a fraction of what rovers create. Rail systems can include sealed undercarriages and fewer exposed moving parts, shielding critical components from dust infiltration and simplifying maintenance in the lunar environment. Range. The distance a lunar rover can cover is limited by the battery. Batteries currently have low energy density. That's why there are no large planes powered by batteries. Add to that the constant zigzagging to avoid divots, slopes, craters, and inclines, further depleting rover batteries and reducing range. Realistically, a rover can cover only tens of kilometres in a day. For example, reaching Shackleton Crater, likely over 10 kilometres away, and requiring a 4-kilometre descent to the crater floor, could consume much of a crew's day, leaving little time for productive tasks. A rail network, as proposed by Northrop Grumman, eliminates these range limitations. Trains draw continuous power from electrified tracks, overhead lines, or integrated solar panels. Honeybee Robotics, a Lunar 10 partner, supplies deployable masts called Lunar Sabre, with the largest version delivering up to 100 kilowatts of electricity day or night, while also providing lighting, communications, and surveillance along the route. Without the need for heavy onboard batteries, trains are lighter, faster, and capable of long-haul transport across the lunar surface. The absence of air resistance further boosts efficiency compared to Earth-based railways, enabling rapid, reliable travel to distant sites like resource-rich craters, supporting both scientific and commercial missions. Payload capacity. The Moon's low gravity reduces traction, severely limiting the cargo rovers can carry. For example, the Apollo lunar roving vehicle managed only 490 kilos, including crew. Commercial lunar mining, which could involve moving millions of tons of regolith for processing and disposing of slag, far exceeds rover capabilities. Heavy loads risk rovers sinking into soft regolith or tipping on modest slopes. Scaling up rovers to carry more requires larger, heavier batteries, which worsens dust issues and further restricts capacity. Rail systems, by contrast, excel at heavy transport. Trains distribute loads across multiple coupled cars, supported by pre-prepared tracks with sleepers and embankments. This allows massive payloads. Northrop Grumman suggests up to 125 tons per train. The track stability in low gravity makes trains ideal for transporting mined regolith or water ice from craters to processing facilities, enabling scalable commercial operations. Rolling resistance. Rovers drive over soft, compressible lunar soil, causing wheels to sink or deform on the surface. This creates high rolling resistance, much like driving on loose sand. A rail system uses hard, low-friction interfaces, such as metal wheels on metal rails, reducing rolling resistance to near zero. Northrop Grumman's design makes use of sleepers and embankments to distribute loads, resulting in low-energy transport of large cargo volumes over long distances. Surface wear. Repeated rover trips further degrade road surfaces, creating ruts and stirring up dust. Rail systems minimize wear by concentrating contact on durable tracks, which can be made from locally sourced materials via in situ resource utilization. Northrop Grumman's study includes robotic inspection to monitor and repair tracks, ensuring long service life for rail infrastructure. Recurring costs. Rovers suffer from constant wear, needing repairs or parts replaced often, or even full vehicle replacements, leading to costly downtime. As lunar bases grow, and activities like mining or scientific exploration expand, more rovers are needed, increasing repair and road maintenance costs. While building a lunar rail network does involve high initial costs, the running costs are much lower. This makes rail ideal for supporting lunar commerce, moving cargo, crew, and equipment between bases, outposts, excavation sites, and scientific areas. Building the lunar rail network. Building a lunar rail network requires specialized equipment suitable for the Moon's harsh environment. Northrop Grumman breaks the equipment down into 4 segments. Construction and maintenance equipment. Construction vehicles ranging from half a ton to 2.5 tons would be used. These vehicles perform surveying, excavation, hauling of regolith, compacting, assembly and inspection operations. In addition, a crane vehicle will be needed. For maintenance, specialized vehicles perform infrastructure inspection, weld repairs and component replacements, ensuring the rail network remains operational with minimal downtime. Rail track infrastructure. The rail network's foundation requires robust infrastructure to support heavy loads in low gravity. Embankments and bridges, constructed to level terrain and cross craters or uneven surfaces. Sleepers, fabricated from lunar regolith using 3D printing, with companies like Icon developing this technology for lunar applications. Rails, fastenings and switches, produced in a lunar foundry, such as those being developed by Cis Lunar Industries, a Lunar 10 partner, which processes local materials into metals for durable tracks. And supporting systems, communication, power, navigation and surveillance infrastructure powered by solutions like Honeybee's Lunar Saber masts. Rail station infrastructure. Rail stations serve as hubs for operations and logistics, including substations and storage, power substations and storage tanks for resources like fuel or water, loading docks and maintenance depots, facilities for cargo handling and vehicle upkeep, warehouses, built with technologies like Icon's large-scale 3D printers, suitable for lunar construction, command and control, equipped with sensors, control electronics, and data analytics for real-time management, and traffic control, supported by lunar masts providing live data on train movements, ensuring efficient scheduling and safety. Rolling stock. The rolling stock, trains themselves, form the backbone of the network, designed for modularity. Components, motors, brakes, wheel sets, frames, suspensions, couplers, and bogie attachments all optimized for lunar conditions. Transport assemblies include tankers with at least 5-ton capacity, hoppers and flatbeds, tailored for carrying regolith, water ice or equipment. The absence of air resistance and low-friction rail interfaces improve efficiency, allowing trains to handle massive payloads, up to 125 tons, for long-haul transport across the lunar surface. Building the lunar rail network in phases. Northrop Grumman proposes a phased approach to rolling out a lunar rail system. Let's look at the phases. Phase 1, Minimal Viable Experiment, a 200-meter test track. The Minimal Viable Experiment, or MVE for short, aims to prove the feasibility of building a rail track using locally sourced materials, demonstrating commercial in-situ resource utilization. This phase, expected to take 1 year, includes 4 key stages. 1. Resource extraction. Develop capabilities to mine, excavate, and process lunar regolith into materials suitable for rail construction. Technologies from partners like Cislunar Industries enable foundries to produce metal ingots, rails, and sleepers from regolith, slag, or recycled materials like scrap from disused landers or rovers. 2. Infrastructure construction. Prepare the ground through leveling, grading, compacting, and sintering to create a stable base. Lay sleepers, potentially 3D printed, and place metal rails, integrating power nodes, communications, and lighting. 3. Rail transport demonstration. Construct a flatbed carriage and a demo tanker to transport goods and fuel across a 200-meter track, likely built near a mining site to showcase regolith delivery. And 4. Commercial fuel sale. Execute the first commercial sale of lunar-derived fuel, validating the system's economic potential. This phase proves an operational rail track can be built from locally sourced materials. Phase 2, Scaling to Operational Use. Phase 2 matures the rail architecture over 2 years, transitioning the MVE track into an operational system that generates revenue. Key activities include upgrading to second-generation engines and carriages, including improvements from lessons learned in Phase 1. Improving construction equipment for faster, more efficient track laying, expanding the test track to support early mining and foundry operations, refining the system's design and operations. By the end of Phase 2, the rail track is fully operational, capable of supporting commercial activities like resource transport. Phase 3, Pilot Expansion, 5 to 15 kilometers. Phase 3 extends the network to 5 to 15 kilometers, connecting to high-traffic launch sites. This 1-year phase focuses on integrating the rail with key lunar infrastructure, such as landing pads, to support frequent missions and increase operational capacity. Phase 4, Network Growth, tens of kilometers. Over another year, Phase 4 expands the network to tens of kilometers, adding routes to other settlements, outposts, or resource extraction sites. This phase scales the system to serve multiple lunar facilities, enhancing connectivity and supporting a growing lunar economy. Phase 5, Full Operational Expansion, hundreds of kilometers. In the final phase, spanning 3 or more years, the network grows to hundreds of kilometers, linking additional settlements across the lunar surface. Expansion is driven by commercial justification, ensuring each new route supports economic activities like mining, scientific research, or tourism. This phase establishes a robust pole-to-pole rail system, enabling mass transit of resources and crew. Selecting the site for the Lunar Rail Network. A critical question for Northrop Grumman's Lunar Rail Network is where to lay the tracks. The Artemis Base Camp, located near Shackleton Crater and close to the Moon's south pole, is a prime location due to its proximity to resource-rich areas. Northrop Grumman provides detailed maps for the rail network near the Artemis Base Camp. However, the tracks will not run directly next to the camp, as it's situated on elevated terrain, unsuitable for rail construction. Instead, the initial 200-meter test track for the Minimal Viable Experiment is planned just north of the camp, close to Shackleton Crater, to leverage nearby mining opportunities. The study proposes 2 reference plans for track expansion, extending north and west of the base camp in phases. By the end of Phase 4, the network will span 28 to 31 kilometers, connecting key sites such as Shackleton Crater, launch pads, and landing zones. This expansion ensures efficient access to resource extraction sites and critical infrastructure, supporting both scientific and commercial activities. While the plan is promising, cost remains the decisive factor in moving the project beyond the initial stage. A ride on the Lunar Rail Network will cost you $8 million. Riding the Lunar Rail Network comes with a hefty price tag. Initially, each trip will cost around $8 million. However, by Phase 5, this is expected to drop to $2.5 million per trip, making it more cost competitive as the network matures. Northrop Grumman in this graphic illustrates the rail network's efficiency in transporting mass compared to alternatives like rovers. The data shows that over time, rail becomes far more cost effective. By Phase 4, the lunar rail network is the cheapest method for moving large volumes of cargo, such as mined regolith or equipment, across the Moon's surface. Challenges in building a lunar rail network. Constructing a lunar rail network faces challenges due to the Moon's unique environment and the scale of the project. Let's look at the problems and some potential solutions. Demand and resource harvesting. A rail network requires demand to justify its construction. Without habitats, mining sites, or scientific outposts, there's little need for rail transport. The primary driver is lunar resource harvesting, which could involve excavating and processing thousands to millions of tons of regolith for water, propellant, or helium-3. Once mining operations are established, they generate both the demand for rail and the raw materials, such as regolith byproducts, slag, or scrap metals needed for construction. A lunar foundry, such as one proposed by Cislunar Industries, would process these materials into metal rails, while 3D printers fabricate sleepers from regolith, reducing reliance on Earth-based supplies. Extreme temperature fluctuations. The Moon's temperature swings from below -200 degrees Celsius at night to over 120 degrees Celsius during the day cause rail tracks to expand and contract. This thermal stress could warp or misalign tracks, disrupting train operations. Careful material selection and engineering designs, such as expansion joints or thermally resistant alloys, are needed to mitigate the issue. Wheel rail stress. Northrop Grumman highlights high stress between train wheels and rails as a concern, driven by the abrasive lunar environment and vacuum-induced wear. Selecting durable materials for wheels and rails is critical to ensure a long lifetime and reduced maintenance needs. Lunar soil and moonquakes. Understanding lunar soil's behavior under compaction is essential for creating stable track foundations. Additionally, while not mentioned in the study, moonquakes pose a potential risk, especially in later phases with hundreds of kilometers of track. Seismic activity could destabilize tracks, requiring reinforced embankments or flexible track designs. Reduced gravity and traction. The Moon's low gravity reduces traction, making trains prone to slipping during starts, stops, or acceleration, similar to driving on ice. This is a big problem on curved tracks, where centrifugal forces push the train outward, risking derailment. On Earth, a train's weight and track banking, called the cant angle, counteract this force, but the Moon's low gravity requires alternative solutions. Increase cant angle. Steeper banking relies on track shape to keep trains stable, but it complicates construction and may limit sharp turns. 2. Limit speeds. Slowing trains in curves reduces centrifugal force, improving safety but increasing transit times, which undermines the rail's efficiency. Or 3. Build bridges. Instead of navigating around large craters, constructing bridges allows trains to travel in straight lines at full speed, avoiding curves altogether. However, this adds complexity and cost to construction. This traction and curve challenge is a core engineering hurdle. Curves are inevitable on a crater-strewn lunar surface, and slowing trains diminishes the rail network's advantages over rovers. Engineers must balance track design, material choices, and operational strategies to optimize performance. Final thoughts. Wherever humans settle, a rail system seems to follow. On Earth, mining and excavation rely heavily on rail to transport vast quantities of material efficiently. Will the Moon follow suit? Given the emphasis on resource harvesting like regolith, water ice, and helium-3? What do you see as the biggest hurdles to building and operating a lunar rail network? Is it the engineering challenge of track banking in low gravity, where reduced traction complicates curves? Or is it the uncertainty of demand, with the need for established mining sites and habitats to justify the investment? Perhaps the complexity of robotic construction in the Moon's harsh environment. Extreme temperatures, abrasive dust, and soil uncertainties poses the greatest obstacle. Share your thoughts and opinions in the comments below. Thanks for watching. If you enjoyed this space video, consider buying me a coffee to help fund more episodes like this. The link is in the description. Space News Live is on Saturday evening or Sunday morning depending where you watch from. The live stream is a great way for you to share your thoughts and opinions on the videos I posted this week or on any space topic in general. I highlight the most thought-provoking comments on videos I've received, along with late-breaking space news and previews of upcoming content. If you've got the time, please tune in and say hi. Be sure to like and subscribe so you'll see our upcoming videos. We make videos every week covering the space industry with an emphasis on the smaller space startups that aren't covered so well on other channels. See you soon.